Okay, in this video we're going to talk about operational amplifiers, known simply as op-amps for short. Up to this point we have been making circuits using passive components, which can be used to make things like filters and other sorts of circuits. But they're limited by a fundamental issue, which is you can't amplify the amount of power going through an RLC circuit or a circuit composed of passive components. And in fact, op-amps are the most common element used for manipulating analog signals because they are known as active components, which means that they have a separate power supply which can be used to augment, amplify, or increase the amount of power in a given circuit. Now, an op-amp, which we generally draw with a triangle like this, is a 2-input, 1-output device. And basically, you have one input, which is known as the non-inverting input, which is designated with a plus sign, and a second input, which is the inverting input, which is designated with the minus sign. And basically, the op-amp takes the difference between the input and the output and multiplies it by some gain, which we'll call G, and it produces some voltage. So we'll write V plus, and we'll write V minus here. Oops, V minus. And basically the output, V out, is equal to G, the gain, times V plus minus V minus. Now for the sake of completeness, we'll add two more connections. One is the positive voltage supply, and one is the negative voltage supply. And these are often left out on electronics diagrams, but of course the op-amp won't function at all if you don't provide it with the positive and minus and negative power supplies. This is where the extra current is drawn from in order to produce the large gain that is seen at the output voltage. Now, most op-amps are not used in a open loop configuration like we see here. They're almost always used in a closed loop configuration where the output voltage is fed back, possibly through some resistors, to the inverting terminal, the inverting input terminal. And what this does is it allows us to calculate using standard formulas what the actual, or allows us to adjust the gain of the op-amp by putting in resistors and other components as necessary. Now for real op-amps, of course, the equations to calculate the exact gain and the exact output voltage are rather complex, but in general we can use an idealized operational amplifier, and in doing so that gives us a very good approximation of what the behavior of the op-amp will be. And then later on you can go and calculate what the second order effects are by using non-ideal components. So for an ideal op-amp we assume three things. One is that the gain G in the open loop circuit is infinite. The second one is that there is actually no input current. And what I mean is when a voltage is being supplied at the V plus or the V minus terminals here or here, we assume that none of the current actually goes into the op-amp. In fact, a very small amount goes into the op-amp, but there's a very high impedance on the order of mega ohms impedance, so it's not very much current at all, and it greatly simplifies the calculations that we're going to do in a minute here if we assume that. We also assume no output impedance, meaning that whatever's coming out of the operational amplifier, VO, is not affected by downstream resistances and such. So when we do this, we end up with what's known as the two golden rules of ideal operational amplifiers. So the golden rules. The first one is that the inputs draw no current. That was one of our assumptions before for an ideal amplifier, so that's not a particularly novel idea, but it will be useful to state it as the golden rule. And the second one is that when connected with negative feedback, so when the output is connected back to the inverting input on the op amp, and there may be some feedback circuitry involved here, that the op amp will do whatever is necessary to make the two inputs, the inputs at V minus and V plus, the same. Now, why would that be? Let's say that we have an op amp as shown, and we have an input V plus going in and an input V minus going in. There, I've magically reconfigured it for you. So let's say that V plus is a little bit more than V minus. What that means is that if we assume an infinite gain, that the output will be very large, in fact infinite, but it'll be very large. And as it comes through the feedback loop, then it will increase the amount of voltage going into the V minus terminal. And basically, this will keep the V out will continue to increase until there is no difference between the V minus and the V plus, because anytime there's a difference between the V